When we have sp3, it means we essentially have 4 sp3 orbitals. So I'll go ahead and I'll draw it a little bit better first. That's not much better. There we go. And so this is an sp3 orbital. Whenever we have sp3 orbitals, we have 4 of them. So I'll go ahead and copy and paste again and paste again. So we have 4 sp3 orbitals. So I'm going to draw essentially 4 orbitals around that carbon. So I'll draw its little tail, and so I'm going to try to replicate the geometry of the molecule over here. So I'll draw an sp orbital, but this time I'm going to go ahead and make it dashed to indicate that that hybrid orbital is going towards the back. And then we have another wedged sp3 orbital. So I'll draw it a little bit thicker to indicate it's coming out at us towards the front, right? And then lastly, we have an orbital, another sp3 orbital in plane. These two are in plane. And this one, I think I can do it better than that. There we go. That's coming out at us, right? So we've drawn the 3 sp3 hybridized orbitals around it. Now we're going to draw the hydrogens. We know hydrogen has only 1 s orbital. There's only 1 electron around or in the ground state of hydrogen. So it's 1 s, and hydrogen is right there. So I'll do the same thing here. It's 1 s. So I'm going to color the part where they overlap. And there is hydrogen, and then again, here's 1 s orbital for the 3rd hydrogen. And color the part where they overlap. And let me actually change these colors to try to make it clear that they're different orbitals. So I'll keep the sp3 hybridized orbitals in blue, and then there we go. And then lastly, bring it a little bit closer so there's more overlap. This is 1 s with a hydrogen there. So now I basically drew all the orbitals in this molecule. And so again, we have the dashed ones going towards the back, the really thick wedged sp3 orbital, hybridized orbital going towards the front. And so I'll draw sp3. There we are. And so we fill in inside the orbitals what type of hybridized orbital it is. Note that I drew sp3 within the orbital. And so if we take a look at what we have so far, this will be the hybridization of the molecule. So let's do another example. It's time. Example 4. Now, we said anytime an atom has a double bond on it, just one double bond, I should say, we're going to have an sp2 hybridized orbital. So I'm just keeping these different colors just so we don't get them confused. So both these carbons have sp2 hybridized orbitals. So let me go ahead and draw the carbons. Now note, unlike the last image where the color difference was the actual orbital difference, here I'm just going to use the color difference as just showing different atoms. And to make that clear, I'll just put this in red instead. Okay, so I have a blue carbon and a red carbon, and I know both of those carbons are sp2. So whenever I have an sp2 orbital, what that means is essentially 3 slightly smaller than the sp3 orbitals, and then 1 unhybridized p orbital. So 3 hybridized sp2, 1 unhybridized p orbital, excuse me. There we go. So now what I need to do essentially is draw that around these atoms. And so what I'll go ahead and do is I'll start to draw. I need around this atom, I'll go ahead and draw the unhybridized p orbital. Both those atoms have unhybridized p orbitals, but I'll just stick with drawing the first one. And so now I'll go ahead and draw. Here is, let's do that a little bit bigger. I don't like that shape. Bear with me. And then, okay, so now let's fill this in. These are the sp2. There are 3 of them. So we're going to write sp2, 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 right? And then we said 1 unhybridized p orbital, and so that's this orbital right here. Let's draw it a little bit bigger so it's not as lanky. There we go. So this is the p orbital right here. It's unhybridized, and we'll see why we need an unhybridized p orbital in a second. Now, same thing with the other sp2 carbon, right? It's going to have 1 unhybridized p orbital. It's going to have 3 sp2 hybridized orbitals. Right? And so that's anything with that sp2 hybridization is going to have 1 unhybridized p orbital. So check, and then also 3 around it that are hybridized sp2. So now that we've drawn in the carbons, let's now add the 1s hydrogens. So let's go to green. There we go. We need to draw. Here's my 1s. There's my hydrogen. Here's my 1s. And there's the overlap. And then there's my 1s. It's a hydrogen. It's a 1s orbital. There we go. And then now what we do is we essentially draw that these p orbitals are overlapping, forming that double bond. All right? And so when I look at this atom, when I look at this molecule, excuse me, I have 2 bonds here in the middle. One of them is a sigma bond. A sigma bond is a single bond. And it has 2 atoms directly overlapping. So direct overlap. What do I mean by that? So here we have direct overlap. The p orbitals don't have direct overlap, right? And so this is going to be a sigma bond, that's going to be a sigma bond, that's going to be a sigma bond, that's going to be a sigma bond, because there's direct orbital overlap. So I'll say sigma here, sigma there, sigma bond there, sigma bond there, and sigma bond there. Now, whenever 2 p orbitals are essentially overlapping, we have now let me use a different color, we have a pi bond. Pi bond is essentially just a double bond. Notice it's the second bond in the double bond. So let's clarify. Here is the pi bond, and the sigma bond is the one in black. So I'll just leave this arrow right here, sigma bond, and then the yellow is the pi bond. There we go. And so now this overlap between the two p orbitals forms a pi bond, which is a double bond. So remember though, this is something very confusing to a lot of students. All of this, all of the overlap of two adjacent p orbitals is one pi bond. So that is essentially, let me draw this carbon, carbon, two bonds, and then there's the hydrogen. This entire overlap is just one bond, not two. That's where students confuse it. This bond right here, I'll color in red, comes from the sp2 orbital overlap, right? And so again, even though there are two heads of the dumbbell, right, it only gives us one a double bond. It's that double bond. So let's actually, for clarity, let us do this to flesh out this concept here a little bit further. What this will look like is here is the sigma bond. So this is the sigma bond. The yellow is the pi bond. And then we would need another pi bond. Let's put it in blue, going in a different direction. So those would form that third pi bond, the second pi bond for the third bond in the triple bond. And so I want to reiterate this point because it is confusing. Everything in the yellow, these two unhybridized p orbitals, is going to just be this one bond in the yellow when it comes to this molecule. Everything in the blue is going to be this bond. And then what's in the red is going to be the sigma bond. So the red, which has this, is that bond in the middle. So when we look at a molecule like this, we can count the number of sigma bonds. There is one sigma bond, and how many pi bonds are there? So if I were to ask you how many pi bonds, the answer would be one pi bond coming from the yellow, and then one pi bond coming from the blue, for a total of 2 pi bonds, right? And so the number of pi bonds would be equal to 2 in this molecule, and the number of sigma bonds would be equal to 1. Hopefully you guys can see that. The red bond is 1 sigma, and then the yellow bond is 1 pi, and then the blue bond is another pi, so you'll have a total of 2 pi bonds. So if I give you something like this, and then I ask you how many, actually let's simplify this example. Getting a little sloppy with my drawings. There we go. All right, so we have 3 carbons here. And now let's take a look. We have how many sigma bonds? Well, we have a sigma bond there, and then we also have a sigma bond there. So we have 2 sigma bonds. How many pi bonds do we have? Again, we have 1 pi bond here, and then another pi bond there for a total of 2 pi bonds. So that's 1, oops, let me get the next one. 1 plus the one in blue for a total of 2. Right? And so that's important. That's going to be a high yield concept. They're going to give you a really big molecule and ask you what essentially is the number of sigma bonds and what is the number of pi bonds. So this type of problem is going to be high yield on your first midterm. So make sure that you get good at this. And we'll do some more examples here in a second. But let's go back to drawing out orbitals. So we drew out 2 different molecules, so CH4, and then also we drew C2H4. Right, now let's keep going. Let's do another example, and then we'll come back to the number of sigma and pi bonds in a molecule. So example, a little closer. Example 4, I believe we're on, or is it 5? It's 5 now. Losing track. All right, so we have this as an example. We've already done that here, but I want to actually flesh out. We've already kind of touched on that, but I want to flesh it out fully. And so let's color code these carbons. So I'll say this one's carbon blue, this one will be carbon green. And so we know whenever something has 3 bonds around it, it's going to be sp hybridized. And so sp is going to basically have 2 little short and stout sp hybridized orbitals, and then 2, I'll do that so well that I want to copy and paste it, 2 unhybridized p orbitals. There we go. And so now when I draw these carbons, so I draw the first one, I'm going to draw 2 sp hybridized orbitals. Let's make this a little bit more. There we go. There we go. So this is sp, that's sp. So check and check. sp and sp. Now I'm going to draw the 2 unhybridized p orbitals. And so to stay consistent with the last problem, I had blue and yellow. So I'll go ahead. There's my P, and this would be in which axis? This is going to be my P in the Y axis. Now I'll draw, actually, there is my P in the Z axis, right? Now I'm going to draw the next carbon. So I put it in green. And I'll go ahead and put the orbitals around it. Let's move it a little bit closer so we can get some overlap. There we go. I have my sp there. Those 2 are overlapping to form my sigma bond. Then I'll go ahead and draw the p in the y axis, so p y, and then p in the z axis. Right? All of this is P. It's not just 1/2 of P. All of the whole thing is P. And so these guys are going to overlap. And then the blue P orbitals in the Y axis are going to overlap. Let me get a little bit clearer so we don't get in the way of things. There we go. And so now when I draw this again, or even if I go back to my original drawing, here is going to be the P overlap in the y-axis, and then that's going to be a pi bond, and then this is also the pi bond. So lastly, in the middle, we have the sigma bond, which is the overlap right here. Right, now we're not finished. We still have two hydrogens that we need to add. And so hydrogens are going to be, and then I forgot the second sp orbital here. And then now I'll go ahead and put my hydrogens. So let's see if I can get I'll just keep it. The green might be confusing. But hydrogen just has a 1s orbital, both cases. And so let's look at my sigma bonds. Remember, anything with direct orbital overlap is going to be sigma. So this is one sigma bond, that's one sigma bond, and that's one sigma bond. The blue up here, all of this, oops, getting too excited. The blue up here is going to be a pi bond. Doesn't have that direct overlap on the same axis, essentially. They're parallel and then they're overlapping. And so the same thing is with this pi orbital. So now, the p orbital in the yellow on the z-axis is going to form a pi bond. And so again, there's that yellow, that's my pi bond. And so how many sigma bonds do I have in this molecule? Let's put them in red. I have one right here, this middle one, and then this last one. So sigma is going to be 3. How many pi? 1 from the blue, orbital overlap, and then 1 from the yellow, orbital overlap. So we have a total of 2. All right, let me erase. There we go. And so now let's try to figure this out, and let's try to give us a heuristic or a shortcut to follow. Imagine you have essentially a certain amount of currency and you're trying to cash that out. So let's say I have, a $10 bill. So that could be 2 $5 bills. That could be 10 $1 bills, right? And so on and so forth. If we have $2 bills from the bank or whatever, we can also play with 5 of those, right? And so it's the same thing with whenever we see a triple bond. Whenever we have a triple bond, so let me draw a carbon here, a triple bond is going to be equal to, there, and blue there, just to stay with my convention. A triple bond is going to be equal to 1 sigma and 2 pi bonds. Whenever I see a double bond, it's going to be 1 sigma, it doesn't matter blue or yellow in this case, and 1 pi. So 1 sigma and 1 pi. Whenever I see single bonds, just going to be 1 sigma, right? And so if I have, let's say, this molecule as an example, there's this example of a molecule in the skeletal structure. So let's go through and kind of flesh out the carbons. How many carbons do I have? 1, 2, 3, 4, 5, 6. Right, and so now I can go through and count the sigma bonds. This would be a sigma bond. There are 3 implied hydrogens here, 3 sigma bonds. This is going to be a sigma bond. That's going to be a sigma bond. The 2 implied hydrogens are sigma bonds. Anything that's a single bond is a sigma bond, dude. So this right here is going to be a sigma bond. There's only 1 implied hydrogen here. So that's going to be a sigma bond and 2 implied hydrogens up here. And then again, that's going to be a sigma bond, right? So if I count them up, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Got 11 if my counting is accurate. Now let's take a look at sigma bonds, or pi bonds, excuse me. I have 1 pi bond here, pi bond, excuse me, there, and another there, and then a third one that comes from this triple bond. So my pi bonds, I'm going to have 3 total in this molecule. Right, so a question that will be high yield is basically count the number of sigma bonds and the number of pi bonds in a given molecule. Again, this will be on the first test, but then it will quickly be forgotten because it will be implied knowledge on tests and quizzes there on out. All right, so it's not something that we're going to essentially continue on in the rest of the semester, but you should already know it in case it crops up. Now, revisiting this, I want to touch upon a couple of things. The first thing is that orbitals have to be on the same axis for them to form a bond, right? Meaning that I cannot, and I'll just kind of ignore a lot of the, what else is going on. I cannot have an MTP orbital in the p axis, or excuse me, in the z axis, bond with a p orbital in the y axis. These two cannot bond. They cannot overlap. They're not on the same orbital. And so we will see this whenever we get a molecule like this. So we have nitrogen. Let's say, I'll put there. We have nitrogen. Nitrogen, this essentially is going to have an sp2 hybridization. So we're going to have an MTP orbital. We're going to have 3 essential sp orbitals, right? And so, excuse me, sp2 orbitals. So let me go ahead and draw this. And so this is nitrogen. Let me see if I can create a little bit of space for it. There we go. Oh, wow, that looks great. There we go. And so here is the challenge with a problem like this. The lone pairs in the sp2 orbital, these form a bond, which is, let's color it. They form a pi bond, which is right there. And then they form a sigma bond, which is right there. This is going to be, I drew this wrong. Give me 1 second. This is sp2, 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 sp2. Right, and then these are hydrogens that are 1s, 1s, right? So here's the challenge. These orbitals are not in the same plane as the lone pairs. So the temptation here is to be able to drop a lone pair in and form a triple bond. That can't happen because these guys are in the PY plane. Let me draw them in blue. But this is in the Z plane. So the sp2 is in the Z axis. So you cannot, let me use a different color. You cannot drop those lone pairs down to form resonance. They're not on the same axis. So that's an important concept to remember. P orbitals will only interact with other adjacent P orbitals that are on their same axis. This will not take place. So let me draw a big X around it. See here in the red, so we can't miss it. That won't happen. They have to be in the same plane. So the PY has to overlap with PY, and the PZ has to overlap with PZ. Again, this becomes important when we have things like this, where we have an sp2 orbital housing the lone pair, but the PY is perpendicular to it, so you can't have resonance. So this is no bueno. It's not allowed, right? And so this is a very important concept because you'll see people making this mistake again and again and again, right? We'll do one last example and we'll conclude. Let's see here. This is example 6. Nope, example 7, excuse me. And we have now we're going to count up the number of sigma and pi bonds. So let's go ahead and say here's sigma. How many do we have? And then here's pi. How many do we have? Every single bond is going to be a sigma bond. So this is a single bond. That's a single bond. That's a single bond. This is a single bond. There's a single bond there before we get into the double bond. There's another one there, another one there, another one there, another there, another one there, another one there. And of this double bond, one of them is going to be a sigma. There's a sigma bond there. And then let's go ahead. This middle bond is also a sigma. So if we count that up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 total sigma bonds. Now let's look at pi bonds. So we have one right here, and then we have another one right there, right? So that's 2. And then for the rest of them, I'll just keep it in blue since it's only. So that's another one. There's going to be another one. There's going to be another one. And there's going to be another one. So essentially, we have a total of, let's count them up. 1, 2, 3, 4, 5, 6. So 6 pi bonds. One of them essentially is yellow, but that's just in the triple bond just to indicate that there is an additional sigma bond. I can even color it in blue so that way you guys can not be confused, right? And so again, this type of problem will be high yield. You'll see this on quizzes and exams.